Okay, hello. So this is a video about the topic of simple harmonic motion, or SHM, which is included in further mechanics, so further maths A-level mechanics. It should be mentioned that it's obviously also a topic in A-level physics, and different students will come to this subject with different levels of knowledge. So wherever you are, I hope you find this useful. I'm obviously going to give a brief explanation of the idea, but then focus more on how you solve exam questions. So in terms of the idea of simple harmonic motion. Now you may have learned simple harmonic motion as a formula, really, like something like this: second derivative, maybe like this. The second derivative of a sorry, that's completely wrong. The second derivative of a certain variable is proportional to the variable itself with a constant of proportionality which is negative. Actually, we don't usually see it written like that. We usually see it written with a time variable, so something like this: d2x by dt squared is minus, and then some number here squared times x. So that's a mathematical definition, a defining equation for simple harmonic motion. But what's really going on? Why is simple harmonic motion an important idea? Well, I think the best way to explain it is an example like the graph I've shown you here. Now you may recognize this graph if you've studied physics, because it's a typical graph for force between two atoms. So force between two atoms. What I'm saying is that if two atoms are close together, they will experience a force. They will exert a force on each other. And the question is, what is the magnitude of that force? So what I'm showing in this diagram, which you may well recognize from physics, is repulsion. Repulse means pushing away, yeah? So the two atoms, when x is small, that means the atoms are close together. If the atoms are close together, they will push each other away. Okay, they won't stick together. On the other hand, if the atoms are further away, you get a force in the opposite direction. You get a force pushing the atoms closer together. So pushing together at a certain distance, pushing away at a closer distance. Now, of course, if the distance is very large, then the force quickly becomes negligible. Basically, the atoms don't even notice they are each other if the distance x is too large. So that's something you've almost certainly seen in a physics textbook if you study physics. But if you don't, it doesn't matter, because what I'm going to explain doesn't depend on that. So the question now becomes, well, the first question that's practically important is the question of equilibrium. For what value of x do the two atoms experience equilibrium? So equilibrium is the point where the force is zero. Yeah? So equilibrium, I'm shortening there, EQBM, equilibrium, when force is zero. Okay? So one thing that physicists have tried to do over the last 100 or 200 years is to develop formulas that allow them to actually figure out what the exact form of this curve. And a big part of that is figuring out when the force is zero. If you have two, I can't think of a good example, two copper atoms. Chemists will probably laugh at my description here, but two copper atoms put next to each other, at what distance will they be in equilibrium? Okay, maybe that's a stupid example, but anyway. So we have equilibrium here. But I want you to notice something interesting about this equilibrium. It is what we call stable equilibrium. And I think that's kind of a key idea behind SHM and why it's important. So what is stable equilibrium? Well, the easiest way to understand it is, imagine you have a ball in a cup or a bowl. Yeah, maybe this is some kind of bowl, and this is like some kind of small steel ball. You drop the ball into the cup. What does it do? It rolls backwards and forwards like that. Now, oh, that's going to, there we go. So after some time it loses energy and it settles here, doesn't it? So this is a stable equilibrium. Why is it stable? Because a slight perturbation, a slight push to one side or to the other side will result in the object going back to where it started. And if you think about that, that's because when you push the object from here to here, the force it experiences, actually its gravity, will push it back to where it started. So this is what we would call a stable equilibrium. Now the opposite, of course, would be the bowl is turned upside down and the ball is put on the top. So this ball on top of this bowl is in unstable equilibrium. So it's unstable because a small push this way will result in it falling far away from the equilibrium. So that's the idea of stable and unstable equilibrium. Let me just remove these scribbles. That's the idea of stable equilibrium. Now I hope you can see that this example is an example of a stable equilibrium. And the reason it's stable is because if we move, so here's the two atoms at equilibrium. Suppose the distance between these two atoms here, whoops, is x0, where x0 is the equilibrium position. If we move the atoms slightly farther apart, that means we're going down this curve. If we move them slightly farther apart, they experience an attractive force which pushes them back together. And if they move slightly closer together, they experience a repulsion which pushes them back to where we started. So this is a stable equilibrium. And if you think about it mathematically, what makes this equilibrium stable is that the derivative is negative. Yeah, the derivative of the force, in other words the gradient of the curve in this region, is negative. So that's an important part of SHM. That's why in the SHM equation we have a minus sign, because we're talking about a stable equilibrium which pushes us back to where we started. Okay, so far I haven't actually shown any connection to the equation I mentioned at the beginning. What's the connection between all this and the standard SHM equation? Well, I think this is where it gets interesting. This is the real reason I showed you all this, is because actually in a case like this we do not have SHM. What we have is something very close to SHM, an approximation to SHM. So what exactly do I mean? Well, let's imagine that we took this part of the graph and we blew it up. In other words, we expanded it. So maybe I've got an x-axis here. Let's make that a straight line. And okay, the y-axis will be off here somewhere, but I'll just draw the curve as we see it here in greater detail. So the curve may be like this, with x0 being this point here. Let's just label it like this. There we go. x0. This is the x-axis, and this is the force axis up here somewhere. Now, at this point, we can see, well, okay, this is a curve, it's not a straight line, but by the same principle that calculus allows us to find gradients, we can argue that if the changes in x are very, very small, then the curve here looks similar to a line. So the force as a function of x is approximately linear. So let's say f of x minus x0 is approximately k x minus x0. Now what do I mean by that? Do you see? So I'm saying that this is approximately a straight line. So if we take the variable x and change it to another variable, let's say capital X equals little x minus x0, so that the origin is effectively shifted to the equilibrium position, then the variation of force with position, according to this new variable, is something like minus k squared x. Yeah? So here k squared, because I want this to be a positive number, and minus, it's important that the gradient is negative, because as I just mentioned, that's what makes it a stable equilibrium. And maybe I should be clearer here that I mean f as a function of x. And now I hope you see how SHM enters into this. SHM is the natural result of this set of assumptions under stable equilibrium. So we're getting f of x according to Newton's second law. So therefore, because of Newton's second law, we can say that the mass times the acceleration, now let's be like this, is equal to minus k squared x. So we get d2x by dt squared. By the way, if you're not used to this notation of two dots, it just means second derivative with respect to time. So this is the equation of SHM. It says that the second derivative is proportional to the second derivative of a certain displacement variable is proportional to that displacement variable with a constant of proportionality which is negative. Okay, so we'll talk more about the constant of proportionality in a moment, but maybe I should also mention this issue about x minus x0. It's worth knowing, and this is something people maybe are not so familiar with, that if we make a change of variable, so we start off with the displacement variable x like this, and we change it to another variable, well, because of the linearity of the differential operator, it follows that d2x by dt squared equals d2x, d2 little x by dt squared minus d2 by dt squared of x0. And this is 0 because x0 is a constant number. Now I'm just mentioning that. It doesn't really have to affect your thinking too much. It just allows you to remember that when we make a linear substitution of displacement variables, we don't affect derivatives. So that's the SHM equation. Now I know this presentation is a bit abstract, maybe it's a bit complicated, especially if you haven't studied the physics before. But I hope you will see later, as you go through examples, that this way of thinking about it is very logical. And in particular, it will help you with the fact that many questions are about approximation. So some of the questions on the exam are direct, simple SHM questions. Other questions are about how we can make approximations to the motion of a particle using this SHM model. Okay, now let's talk a little bit about the solutions of the equation that we've just derived. So let's rewrite the equation as follows. d2, and here I'll just use an ordinary x, by dt squared, so the second derivative of x with respect to time, is equal to minus n squared x. Now n can also be written as omega, and I'll put in quotes angular velocity, because it's actually the angular velocity of the associated circular motion. And if you don't know what I mean by associated circular motion, don't worry too much, but you can find information about that in the Bostock and Chandler book, Green book, and in other places as well, such as the notes that some of you will have. Now then, what about solving this? What is going on here? This kind of equation is not, of course, like the kind of differential equation, I don't know, like this, which you may have solved in P3. Here you would use what's called separable variables. Separate the variables, which really just means integrate the equation. So something like integral 1 over x dx equals integral dt, just to remind anyone who's forgotten. That's how you do problems like that. But here we have a different kind of equation. We have we have a second order differential equation. Now this is something that you will study in further pure. So further pure, and it's unfortunate if you haven't studied this yet, because if you haven't, you're going to study it very soon. But assuming that people are just using this video for revision, then they should already know this. So in further pure, you learn how to study it. You learn how to solve problems of the form, let's say a d2y by dx squared plus b dy by dx plus cy equals maybe some function of x or something like that. That's the most general case that you solve in further pure. This is a very simple example of that, and if you know the theory of that, then you'll know that we have what's called an auxiliary equation, and in this case the auxiliary equation is something like u squared plus n squared equals 0, so that u is plus or minus in. Now there's a whole theory associated with that. I don't want to go into it here because it will take too much time and it will not be the main topic. So I'll get rid of all this, and let's just say that even if you didn't know the theory, you could at least verify that the right kind of solution to this is, what am I doing? Oh yeah, is sine t or cos t. Well, sine nt or cos nt. So what do I mean? I mean that if you look at these two functions, they have a very special property. If you take this and differentiate it with respect to time once, you get cosine nt times n, according to the chain rule. If you then differentiate this with respect to t, so in other words differentiate this twice, you get another factor of n squared. You get sine nt, but you also get a minus sign. So you get minus n squared sine nt, which is the second derivative of sine nt. So we can already see that this specific function is at least one possible solution to this whole equation. Yeah? So x equals sine nt does solve this equation. And interestingly, cosine nt also solves it, as I'll verify now. That gives me minus n sine nt. Differentiate that means the second derivative of that gives me minus n squared cosine nt. So again we see that minus n squared times the original function is the second derivative of the function, so this is a second possible solution to this equation. So again, if you don't know the theory of second order differential equations, you can at least verify and understand that these two functions are possible solutions. And you should also understand that because this is a second order differential equation, then we're going to get two integration constants. So to put that crudely, it's like saying take this equation, integrate both sides with respect to t. d2x by d2 squared dt equals integral minus n squared x dt, even if you don't know how to do that, because this is x, not t. Yeah? I must emphasize, you can't actually solve the problem in this way, because this is x and this is t. Yeah? But whatever answer you get, you're going to get one integration constant from the first integration, and then because this side is dx by dt, isn't it? Because the integral of the second derivative is the first derivative. So to get x, to get the value of the function x as a function of t, you're going to have to integrate this again, you see, minus n squared x dt, like that. So here you're going to get a plus c, and then you're going to integrate again to get another c. So whether this is new to you or not, I hope it's fairly obvious. It's not very obvious, but fairly obvious that this process has to give us two constants. You can think of it as two free variables. So solving a second order differential equation gives you two free variables or two unknowns. So I want to really emphasize that fact because that will be very important as we go on. So two constants or two unknowns, and that corresponds to the idea that we have two possible solution functions here. So the general solution could be written as, maybe the easiest way to understand it, a sine nt plus b cos nt. And this is a valid way to write the general solution to the equation. However, it's not the most useful way, because what you should remember from P3 is that when we write something like 5 sine 2x plus 12 cos 2x, this can be written in a different way. It can be written as maybe 13, which way round is this? Sine, what am I doing? Sine 2x plus, okay, I'll have to use the actual full, oh yes, of course, I remember now, yeah. If you remember from P3, the way to write this as a single function is to say, okay, there's some angle, let's call it alpha, so that cos alpha is 5 and sine alpha is so something like cos 5, sine 12, and 13 is the other side of the triangle. So 5 sine 2x plus 12 cos 2x is identically equal to 13 sine 2x plus alpha. That's right, isn't it? Yeah. So here you would get sine 2x cos alpha. So cos alpha is 5 over 13, gives you 5 sine 2x. And then it's cos 2x sine alpha, giving you the right formula here. So I hope you remember that trick for rewriting a combination of sine and cosine as a single trigonometric function. And I hope you also remember that it can be done in more than one way. Yeah, so you can rewrite it as a cosine or a sine. So in fact, in general, we can write this x, remember x is a function of t here, as a combination. Now here I'm going to write a, I'll talk about that in a minute, times a cosine, it could be a sine, but I'll use a cosine, nt, it needs to be n, it needs to be the same multiple as here, excuse me, plus another angle, epsilon. And I would say that in most cases it's better for a student to remember this formula as the general solution. This is the general solution, and what that means is that every example of simple harmonic motion can be written like this. And I want you to notice what variables exist here. T time is fixed, x is the function we're looking for, x is the displacement of the object as time varies. The other variables, n defines the frequency or the period of the simple harmonic motion, a defines the amplitude, and epsilon defines what's sometimes called the phase shift. So I think it's very useful at this point for me to show a clear diagram of how that works. Let me first remove this example, which we'll look at in a minute. Let's give ourselves a bit more room. Okay, so we're going to draw a picture representing that. Maybe more than one picture, because this is really an important one. So let's have a nice big graph. Bear with me while I set this up, and this will have to be quite a long one. There we go. Hopefully that's okay. Okay, so remember what we're drawing on these graphs is we're drawing the variation of a displacement variable with time. So the independent variable is always time, and here's the displacement variable we're dealing with. Now let's think about what this should look like. We know we're dealing with a trigonometric function, so we have that basic shape. What else do we know? A is the amplitude. So you should already understand the idea of amplitude is that amplitude is the maximum and minimum values of the function. And on the other hand, here we have cosine of nt plus epsilon. Now let's suppose, for simplicity, let's say epsilon is 0. Then what are we going to get? We're going to get a cosine wave starting here, going down to the negative, and then coming back up, and then and so on and so on. I won't draw too many. So dot dot dot. That's going to continue forever. And here, what will this point be here? This will be one period. T is the period. Now what is the period? Well, of course, if n is 1, then the period is 2 pi. So the period is 2 pi over n. And that's something you should know, although in physics you will have learned it as 2 pi over omega. So this is the case, let's maybe give a little annotation. This is the case epsilon equals 0. Well, what would happen if epsilon were a different value? Well, it would just shift the graph. For example, suppose epsilon is minus pi over... I'll use a different colour for this. Let's use red to represent epsilon equals minus pi over 3, just as an example. So if epsilon is minus pi over 3, then when nt is pi over 3, sorry. So let's give that example. When nt is pi over 3, then pi over 3 minus pi over 3 gives 0, and we get a. We get the top of the wave. So when t is pi over 3n, whatever that is, we get the top of the wave. Now when t is 0, then we get cosine of minus pi over 3, and we know that cosine of minus pi over 3 is cosine of pi over 3, which is 1/2. So this red curve will start at 1/2, and it will go up to a maximum when t is go up to a maximum when t is pi over 3n. So maybe that's a bit difficult to figure out. See, of course, without specifying the value of n, it makes it a more general case. But the general idea is that this represents a phase shift. Okay, so everything I said there should be fairly familiar to most students in various forms. I won't go into too much detail now. I suppose the other thing I want to say is that I've circled this in red as being the standard general solution, but there's absolutely nothing wrong with writing a general solution like this. Because after all, the difference between sine and cos is just that cos theta is sine pi over 2 minus theta, and vice versa. Yeah. So it's just a question of a different phase shift. If the phase shift is different, this is also valid. Either way is fine. Okay, now I'm not sure, but I think what I've told you is more than enough to at least understand the basic principle. So here's a question that discusses the basic principle. I think it's fair to say. Here we go. A point P moves on. Now this, by the way, is a real exam question from maybe 2003, I think. But it was question 1, so it's quite a short, simple question. Although I have noted that according to the examiner report, quite a lot of students had trouble with it. And in fact, I remember students asking me questions about this one. So do try it on your own. See if you can do it without my help. And pause the video, try to do it, and then come back. Excuse me. So how to do this question? Well, the first part of the question you should find very easy. It's a very straightforward point, and of course there's only one mark. So here all we have to do is take the derivatives. Now I'm going to use dot notation. X dot means dx by dt. I'll just differentiate this formula. I'll get minus 36 sine 3t plus, minus 15 sine, dear oh dear, rushing, minus 36 cos 3t, and then minus 15 sine 3t, and x double dot the second derivative of x with respect to t, I need 3 times 36, that's 108 sine 3t, and then it's minus 45 cos 3t, just using the chain rule in each case. Now just rewriting this in terms of 9, I will get 9 12 sine 3t minus 5 cos 3t, and it follows that that can be written as okay, so that's that's 9 times minus which way around is it? Ah, yeah. So it's minus 9 times x minus 12, isn't it? Yeah, which is what we want. Okay. Now that's part 1, and it's very simple. But part 2 is where students had a lot of trouble in various different ways. First of all, define simple harmonic motion. So this is not usually asked on the exam, but if it is, they're just going to give you 1 or 2 points to give a simple definition. So if x is displacement from equilibrium, we could say of an object or of a particle, but maybe not necessary, from equilibrium and x double dot is minus n squared x, let's say where n is a for some constant real number n, so I'd better say displacement of p, some particular object p, then p performs simple harmonic motion. I'll just write SHM. So this is one way to write it. It would be advisable also to give a diagram, not necessary perhaps. Something like this, where this is the variable x, and this is the actually that diagram is not only too small and difficult to read, it's also slightly inaccurate, so I'll draw it again. Okay, so if you are going to draw a diagram, make sure somebody can read it. X equals 0, here's p maybe up here. Now I'm actually going to draw this representing acceleration and give the name of the acceleration variable, and then I'll illustrate x as being this distance here. So x is a variable, this is where x is 0, this is the acceleration, which is the second derivative of x. So if I draw the acceleration vector in this direction, then its value is negative, so actually the acceleration is always towards the center or towards the equilibrium position. Okay, don't worry too much about that, that's not the important part of the question. This is the important part. P is describing this motion about a fixed point A. Give the x-coordinate of A and find the period and amplitude of P. So there's 3 things we need to know. First, we need to figure out the position of A, the x-coordinate of A, the period of this SHM, and the amplitude of this SHM. Now we already know, oh sorry, I've forgotten an important part of the question. Show that P is describing this motion about a fixed point A. So I need to show that P is performing SHM. So we know already from the first part of the question that d2x by dt squared for p is equal to minus 9x minus 12. So does that mean that we have already shown SHM? Is this an SHM equation? No, this is not an SHM equation. Okay, and the reason is that the second derivative is not proportional to x because we have this constant value 12. So how do we deal with that? We just define another variable. Define y equals x minus 12. Then d2 x by dt squared equals minus 9y. But x is just y plus 12. So d2 y plus 12 by dt squared equals minus 9y. Well, therefore d2y by dt squared plus d2 by dt squared of the function 12 is equal to minus 9y. You know, I'm writing this in great detail, but you maybe could skip one or two of these steps. And this is equal to 0 because 12 is a constant. It doesn't vary with t, so this derivative is 0. And by the way, this step is exactly what I mentioned earlier about because the differential operator, in other words, differentiation itself is linear. It means that we can split sums y here. Split this into two parts, but you don't obviously have to prove that in a question like this, so they just expect you to write something like what they're really looking for is for you to change the variable. So d2y by dt squared is minus 9y, which is simple harmonic motion. So that's good enough. Excuse me if my writing's a bit unclear. Now, as I was just saying, what they want us to do at the end here is to find the x-coordinate of A, the equilibrium position, find the period of this simple harmonic motion, and the amplitude. Now, I like this question just because if you really understood how SHM is structured, you should be able to just quote the answers immediately. But I found in the past that students weren't able, in particular they got confused about the amplitude. So first of all, what's the x-coordinate of A? What's the center? What this really means is what's the center of this SHM? What we're saying is here's A. Well, the x variable is like this. Yeah. So P is moving up and down around a center point A. What is that center point in terms of x? Because we want the x-coordinate of A. So you should see that the x-coordinate of A is 12. So we see from our calculation here, center of SHM, which is the same as the equilibrium position, is when y equals 0, which means x equals 12. So x coordinate of A is 12. That's the first part. Now, what's the period of this SHM? So, because d2y, excuse me, my dt squared is minus 9y, that means omega is the square root of 9, which is 3. And so the period is 2 pi over omega, or 2 pi over n if you prefer, which is 2 pi over 3. That's the period. And lastly, the amplitude. What's the amplitude? Well, there's a couple of ways you can approach this, but you should see, actually, that... now, I want to emphasize, you cannot find the amplitude from this equation here. This equation gives you the period, but it does not give you any information about the amplitude. That depends on the setup of the problem. If you remember, when we looked at the general solution of SHM, here we said that there are two constants or two unknowns. The two unknowns are the amplitude and the phase shift. So if somebody gives you the value of n, as we have down here, we have n equals 3, it tells you the period of this graph, but it doesn't tell you how big it is or where it starts. You need other information for that. So in the question we weren't really given initial conditions or extra information, but we were, and this is unusual, we were actually given the original form of x as a function of t. So from this we can deduce the amplitude. Let's now, if we like, we can change this to y. Y is basically the same as x. Maybe we'd do it like that. Yeah. Y is x minus 12. So all we're doing is subtracting the 12 from that formula, and we're getting 5 cos 3t minus 12 sine 3t. Okay, now how can we write this in the general form? So I told you the most useful general form is like that, or sometimes you can write it like this. Obviously these two are not equivalent, you would have to change the phase shift. But what I actually want is the amplitude. So I hope you can see that we can use the same trick that we learned in P3, and I used it just a couple of minutes ago, which is to rewrite this as one function. In fact, I need to use that trick. I don't see any other way to do it. There is one other way, but we'll come back to that. So what trick do I mean? I mean, let's write this as a single trigonometric function. If we write this, we see that r squared must be 5 squared plus 12 squared. And we can also find alpha by writing alpha here and then 5, 12 and 13. So amplitude is 13. I don't know how obvious you find that, but what we're trying to say is that if we write this in its most general, in a single trigonometric function form, I'm getting 13 cos x plus inverse tangent 12 over 5, I think it is. Because there we get cos 3t cos alpha, which gives me 5 over 13, minus sine 3t sine alpha, which gives me 12 over 13. So that gives me the right answer. So this, you could say, is the general, well, it's just another way to write the equation of motion given up here. But it's a more convenient form because it shows me the amplitude. Yeah, the amplitude is the highest and lowest points. So effectively it's telling me, now notice by the way, it's not telling me that the x, if we look back at this formula, it's not telling me the maximum value of x is 13 and the minimum value of x is minus 13. No, it's telling me the maximum value of y is 13 and the minimum value of y is minus 13. So minus 13 is less than y is less than 13, but of course x is y plus 12. So it's actually the case that x varies from minus 1 to, what is that, 25. And it's simple harmonic motion about the center point, the equilibrium point where x is 12. Okay, now it's just worth mentioning that you could have deduced the amplitude in another more physical way, which is that you say to yourself, well, when something oscillates, here's x is 12, here's x is 25, here's x is minus 1, if it's going to oscillate up to there, back to there, back to there, and so on and so on and so on, backwards and forwards, well, we know something special about this point. This is the point where x dot is 0. This is the point where the velocity is 0. So if we looked at x dot here and we set this equal to 0, we would also get the same, we would get a certain value of t what would that work out to? Divide by 3's, I get 12 over 5, yeah. So I get 3t is inverse tangent 12 over 5. And then I could put that into my formula for x to get the right answer. So I'll put ... here because it's a few steps of logic, but you can use that if you want. However, much more important is that you understand how to make these general solution forms, these forms with a single trigonometric function. See, it's more useful to have the equation for x or y in this form because it allows you to actually draw the graph like so, and by drawing a graph you can solve pretty much anything you like about the motion. Okay, so I've gone into that in quite some detail. I think I'll leave it there, and I may well do another video on this topic showing some more difficult questions. So thank you.